Well, guys, we're back on AC 101, AC circuits. We're going to start off with a capacitor, but before I get on this, I want to talk a little bit about the video and calculus. For those who are concerned about it and everything, don't be. It was an FYI for your own information video. Someone had asked me or encouraged me to just do a little something on it since I had used calculus in the first AC video, and at that time I meant to, as I said in this last video, I meant to just kind of touch on what integral and integration is since I had used it. But that's all it is. Was just a video just to kind of introduce you to it. You don't have to know it really. Not for what I will be doing on these videos, not with AC, not with any of the radio theory. I'm not here to teach engineering per se, and nor am I here to teach calculus. Just to do calculus would be at least 3 1-hour videos a week for a year to get through the first year of calculus. So we will not be actually doing it. As some suggested in some of the other comments about the other questions about why you need calculus or anything. It is necessary in the engineering and science fields to work out problems, to do those fields. But for the basic theory, no, it's not. I might throw some examples in. They will only be examples. You don't have to know them. You don't have to even pay attention to them. I'm not sure yet, but I might at some point throw an example now and then. Don't worry about it. It serves nothing more than just to show you that, yeah, it's there. The math that will be in this on AC will be algebra. Okay. That's the greatest it'll be. And it's basically just formulas and stuff. And I will probably actually just do the algebra anyway if there's a point where we have a formula and we need to solve for one of the other variables that's in that formula. I will already rework the formula to solve for it. So, and give an example of that. And true, to answer another comment on here, the basic theory of calculus, or calculus itself, is simple, but the other parts of it, the algebra, is not. There are calculus problems that the algebra gets pretty intense. So for anybody who is really truly interested in calculus, who doesn't know it, wants to learn it, I really suggest, at least in this country, I do not know, in the U.S., I don't know about any other countries, but I know in this country, pretty much anywhere you live in this country, there's a local community college of some sort, junior college, 2-year college, and they're all of them should be reasonable on cost. You could go there and take calculus courses. You take a year of calculus there. It'll probably be broken down in calculus 1, 2, and 3 or something of that nature, depending on how they're operating their year, whether it's on a semester or term basis. But the one thing I will tell you is, if you're not strongly versed in all areas of algebra, college algebra, then it would be advantageous to take their their algebra courses first, to get either a refresher or get good at the algebra, because you will need it as you move along in calculus to do a lot of the problems. But that being said, and there are other videos about calculus on YouTube. Just do a general search in the search bar, just calculus. It's basically all you got to do, and it'll bring up a whole bunch of videos. I have never watched any of them. I don't know what all they entail, but you could do that. And the other thing you can also do is you can go to your local library. They should have calculus books in there, that both from high school level as well as college level, that you can check out and kind of work through it on your own. In any case, you will not need it as far as AC goes, or as far as anything I teach. I just did that video just to show you what the integral was and the derivative. So that's all. Now, hopefully I didn't take too much time. I don't know how long this is going to take. I've resorted back to give myself a bulletin list of stuff I need to get through. Here it is. So first thing will be dielectric action, and hopefully we can get through this. Otherwise this is going to be a two-part video. Anyway, what is dielectric action? Well, first and foremost, any capacitor has some form of dielectric. Now it could be air, whereas an air capacitor, like your tuning condenser that you would find in a radio, that would have it just opened the air, there's nothing else between the plates. Or it can be any number of materials. In the old capacitors that you will find in these old radios and TVs, anywhere from a wax paper to an oil paper to mica, glass, ceramic, flint, as well as in electrolytics, electrolyte, which actually the electrolyte is actually one plate. It's not actually the dielectric. There's a paper in there that gets soaked up with the dielectric. That makes up the actual dielectric. More modern caps that you would use to replace, it's some form of plastic. It's a polymer of some sort. All polymer means is plastic, basically. Polymer is just a fancy word for a very long molecule, or what they call a chain molecule. It's extremely long, and that's what makes plastic able to be flexed and moved and stuff. But it'll be some form of plastic, various different types of plastics used. Of course, there's Mylar and several others out there. But the dielectric action is the unique thing. If I have a capacitor, and hopefully this board is working for me, or my pins are. Here's one plate, and in between it we have the dielectric. This is extremely enlarged, by the way. There's the other plate, and we hook this to a battery, and come on, work. Bear with my pins. I think it's about time to get them replaced. Anyway, and plus, minus, as usual. We can put a switch in here if we want. So, I'm going to try a different pin. I'll try green, see if it'll work better. It could be the board too, I don't know. When the switch is closed, or not closed, I mean when it's open, Of course, you got your metal plates and stuff, but inside the dielectric, you know, we're going to draw some very large atoms. We'll put a little dot here for their nucleus. There's a heck of a lot more atoms in this in there, but bear with me. It's just for just general consensus of showing you something. Little circles around these guys, evenly spaced, and so on. Okay, that's what, no charge, no nothing. Now I come in here and I close the switch. So now immediately we're going to have a positive on this side and negative on this side. We'll have for a short duration of time until the capacitor gets fully charged, there's going to be a flow of current. I don't care which way you travel. We've talked about this before. It doesn't matter where you go, negative to positive, positive to negative. It doesn't matter. It just charge carriers are moving. But in any case, you end up with positive over here and negative over here on the plates. Now what that does is something inside the dielectric. These atoms, called the dielectric action. That's why dielectric does help the capacitance. We're going to show how it does. What ends up happening is on this side we're going to have, we're just going to show one atom here, just one electron here, and then the rest of them is going to be shoved to one end. In fact, that one will probably get a little closer too. Now they're not leaving, they're not moving, so it's not conducting. If it was conducting, I could split an electron or two off of here and jump to another atom or even into the plates if it was a relatively similar material of conduction. No, they don't leave their atom, but they do pull up this way because this plate is positive. The electrons kind of get attracted to it, and on this side, since this plate's negative, they flee. And what that ends up doing excuse me, is making this atom look like it's polarized. To these plates, it looks like this side is positive and this side is negative. And what that ends up doing is with this side appearing, and you've got like hundreds of millions and millions and millions of atoms in here doing this in this dielectric, it makes this side of the dielectric look really negative and this side look really positive, which will draw more negative charge here and more positive charge here, increasing the capacity of the capacitor. So that's dielectric action. Just remember what it's doing here. And we'll kind of get back to it in short order. And it looks like our green pen is doing good. The blue pen kind of died out before, so we're running out of colors here. So let's look at what affects capacitance. That's our next thing on our list, the factors affecting capacitors. We'll look at a very simple capacitor. We're going to start doing some math, or at least showing some formulas. The first thing we're going to do is we're going to show a base theory formula. That capacitance equals charge in coulombs, Q, over applied voltage. So capacitance is basically equal to the amount of charge. If I've got a capacitor, in order to increase its capacitance, I've got to make room for more charge. I've got to add more charge to it. But that charge is related also directly to the amount of voltage that I'm applying to that capacitor. So that's just a base formula. It just, the main thing I want you to understand, that charge and capacitance go hand in hand on that. Now some of the other things that affect it is this little formula. Capacitance equals area divided by distance. Okay, what that basically means is when I got a capacitor here, the area of the plates, and actually the formula will only deal with just one plate facing the other one, just that area. But this area through here, the larger it is, the greater amount of charge I can put on, which means the greater amount of capacity it is. But also the distance here. The closer the plates are, the more they can influence each other, which means the more charge I can put on. The further they're spread apart, the less they influence each other, the less charge I can put on. So that's all this formula is saying, is that the area, the size of the plates, divided by the distance, how far apart they are. So the further apart you spread the plates apart, the less capacitance you can actually put on, or less charge, so less capacitance the capacitor is. The closer they are together, the more. The larger the plate, the more charge you can fit in. You know, it's kind of like the old days. What college kids used to love to do is see how many people can pack into a VW Beetle. You know, well, there's a certain limit. Okay. Well, the larger the plate, the more charge I can get on there, because there's going to be a limit of how much charge I can put on. Alright, these are not needed to be even slightly memorized. In fact, nothing I write down needs to be memorized. Alright, we'll get to the next formula after we talk about the dielectric now. Dielectric constants. It's a number given to any particular type of dielectric, and it's used in the actual formula for capacitance. The larger the number, the greater capacitance, and it goes back to that dielectric action. That larger number means several things, but in a nutshell, you can think of it that it's got a dielectric that's got a higher constant. It has more atoms that can actually have the action happen to, with more electrons in their outer shell or outer orbits that can move around to get the action to happen. So it's based off of one simple number, which is vacuum. You can have a vacuum capacitor, and you actually do. You work with them anytime you work on a radio or a tube radio or tube TV. The elements inside the tube are basically like capacitor plates. They're no different. They're conductors. They're set kind of basically in parallel to each other, a certain distance from each other. They have a certain area. The only thing in between them is a vacuum. Not perfect, but close enough. So they act as a capacitor. Vacuum has a dielectric constant of 1. The next one up is air. It has a dielectric constant of 1.00059, so for all practical purposes, it's 1. Some other common ones that you probably will see or deal with: glass. Where's a glass capacitor at? Picture tube. is a glass capacitor. Has a coating called aquadag, which basically is a graphite coating on the inside and on most on the outside as well. So 2 plates, graphite conducts, 2 plates separated by glass. We have a capacitor there, and it usually is made use of as part of the filter or the only filter to the high voltage. So anyway, glass has around 4.2. Mica runs in the vicinity of 3 to 6, depending on what kind of mica it is. Paper, for the wax paper ones, and when they're talking paper, they're actually talking the wax paper basically, runs 2 to 3.4. Let me see. Now, then your plastics, like, well, basically the plastic, the plastic film caps, and I'll just put plastic, runs in the vicinity of around 2.2 to 2.7. And then water, and yes, there were some water caps made. It's distilled water, and there's a lot of special precautions that have to be done with it. Is extremely high. It's 81. These were more used in you won't see them in the basic any type of electronics you ever look at. They were used in other special circuitry. So that that's just a small sampling. There's still like Mylar, and I think it's like 3 or something around there, and various ones. That's your dielectric constant. Well, it adds to the capacitance because of dielectric action. So we get to our base formula for a capacitor. C for capacitance equals 20 to 0.45 times 10 to the minus 8. Now this is just a constant. It's just a number. What it does is allow all the other different information and variables to be in inches. Okay, that's what this number is actually doing. And this will bring the capacitance out to microfarads. So capacitance is in microfarads. That times K, which is our dielectric constant, so it's those numbers I showed you, times the area, and the area is of just one side of a plate. So if I got here's one plate here, it'd just be the area of one side of it. Right here's the area. Not both sides, because you can have another plate over here, and another plate over here, and another plate over here, and these are connected together, and these are connected together. So it's just one side of one plate is area in square inches. That will be also times n minus 1. It's number of plates. So if you have like 5 plates, then it'd be 5 minus 1, so you have a total of 4 in here, times the area of one side of one plate, times our dielectric constant, times this number. This is all divided by T, thickness, because or distance, it's just basically the thickness of the dielectric, because the plates are right up tight to them, to the dielectric. And in some cases it may be actually painted on, like a lot of micas and ceramics. They actually just paint or deposit the plate right on the dielectric. So this gives our distance, how far the plates are separated. This gives the number of plates that we're going to be dealing with, the area of one side of the plate, our dielectric constant, and again, this number allows this to be in inches and this to be in square inches to get microfarad capacitance. Alright. Now, the next little thing we're going to talk about, and you can pause the video at any time, at any point here if you want to write this stuff down, is the capacitor losses. So, cap losses. Now, all capacitors leak a little. And for the most part, it's so low of leakage that it's not important. It's not even practical to even try to measure it unless they start breaking down. If the dielectric starts to break down, then the leakage will increase, and that's why we have, like the ICL 950B or the various different capacitor testers. But for all practical purposes, leakage is not a big issue. It's a little more of an issue in electrolytics, and in the old days we considered that power factor. Today, ESR, or not ESR, but anyway, it's the effective. Basically, it's just they measure it as a resistance in the capacitor, the effective resistance due to the loss, due to the leakage. So, ESR meters, I'm pretty sure that's the name of them. Haven't used one for ages, and I don't even have one anymore. So, leakage is not, under normal circumstances, anything to really be concerned about with new caps anyway. The old paper caps, you want to test them. Either just go ahead and replace them, or you can test them if you got a tester. Some of the other losses is dielectric loss. So, dielectric losses. Well, the first one is dielectric absorption. And that goes back to where we started at, where the electrons move to one side of the atom nearest the positive plate and away from the negative plate. Okay, that's all fine and dandy, but they don't like moving very quickly. In fact, the higher the dielectric constant is, the slower they are to react. They just, once they move, they like to stay there, and then very slowly, can be a long period of time for them to pull back to their normal position. Not a big deal with DC. Once it's charged up, the cap's blocking the DC anyway. But it is important in AC. But not really bad until you get into higher frequencies in the upper megahertz bands, like very high frequency or the upper high frequency band, and ultra high frequencies and stuff. Then this starts becoming a real of interest. appears as a resistance in the capacitor, because they just don't want to switch back and forth and move all those electrons around very easily. So as the frequency goes up, this dielectric absorption becomes a greater and greater loss. And it actually, in the higher frequencies, is called hysteresis loss. Dielectric hysteresis. Hysteresis is just a fancy word for all practical purposes, and the simplest definition is something that is the measurement of change. How something wants to change. In this case, the electrons switching from one side of the atom to the other side, that flipping, that changing of the polarity on the atom. How much it doesn't like doing that is the hysteresis of it, or how well it does it, and don't do it. The other thing about dielectric absorption that you will find fascinating, if you have a capacitor and you discharge it, it's been charged up, you discharge it real quickly, just put a grounding strap, put a strap across it, screwdriver, whatever, ground it out, short it out, so that you discharge it, and you throw it off to the side. It's discharged, no big deal. Maybe a day or two later, even a couple hours later, depending, you go back and you grab a hold of that thing, and you end up touching both plates, both leads, whatever, however it's made, and you get a shock. Well, you discharge it. Why did you get a shock? It's because of the dielectric absorption. Because they don't like returning back to their original positions very quickly. They stay in those positions, which they will then create a static charge on the plates, and effectively you get a shock when you touch them. If it's had a high enough voltage on it. If it's only got like 10 volts is the only thing it ever charge up to, you're not going to feel anything. But this is why a picture tube will hold a considerable amount of charge on it and will rebuild it up even if you do short it out. So if you're ever working on TV, you pull the picture tube. Before you pull it, you go in there and you short out the tube and get that discharged, and then you pull the picture tube and you set it off to the side somewhere where it's safe. If you come back to it a little later, even a day or two later, be mindful it could have rebuilt up a charge because of dielectric absorption. But that's why a capacitor can rebuild a charge. Okay, and then there's resistance losses. The plates are, they're made out of some sort of material. Most regular capacitors, it's usually aluminum. It's a conductor, but it has a certain amount of resistance, and then the wire leads go into it, has a certain amount of resistance. Not important until we get into a real high frequency. And real high frequencies, resistance starts doing funny things. Alright. One last little thing on dielectric is what is known as the breakdown voltage, or strength. Each type of dielectric has a certain amount that it can handle. Once you go above that voltage, it's going to break down. You can look up the specs on this. You can actually do either a dielectric breakdown voltage thing or dielectric strength thing on the internet. Google it, and you'll find all kinds of numbers for all kinds of things. Basically, errors of, and these voltages I give you is per thousandths of an inch thickness. Air is about 20 volts per 1/1000th of an inch. So if I have 2/1000ths of an inch, it's greater. Glass, 335 to 2000 volts per 1/1000th thickness. And that varies because of depending on the type of glass used. Mica, 600 to 1500 volts. Paper, 1250 to 1800 volts. By the way, the plastic film caps in general is about the same as paper. Porcelain, which is basically 40 to 150. Rubber is about 450 volts per thousandth. So just to give you some numbers on that. Now, let's look at when we have capacitors in parallel and series. So if I have say 3 capacitors parallel, and let's say A, B, and C. When I have capacitors in parallel and I want to find the total capacitance that I've got there, they just add up. So I would take A plus B plus C, give me my total capacitance. So if this is 10 microfarad, 10 microfarad, and 10 microfarad, it'd be 30 microfarads. If it was 10, 10, and 5, it'd be 25, and so on and so forth. Now, why is that? Because effectively what this is, they look like this, and that's how you wire them up, but they're really like one solid plate on each side that equals the total area of each one of these added together. It's the same thing. So that's why when you put them in parallel, the charge current comes down, splits off. As far as the charge is concerned, it sees these areas adding up to make one large cap, effective cap. That is nice. Capacitors in parallel, you just add. Now, capacitors in series, on the other hand, are like resistors in series. So if I've got a cap, another cap, and another cap, hooked in series, they don't add together. Alright, so if I say, well, instead of A, B, and C, let's say C1, C2, and C3. So the total capacitance here of these is C total. Let me move this down just a little bit. Equals 1 over C1 plus 1 over C2 plus 1 over C3. It's the same formula for resistors in parallel, except we'd just put R, 1, 2, and 3 in here. And you can be 4, 5, 6, 7, forever. However many caps you want to put in series. When you got more than 2 caps, this is basically the formula you're going to have to use to figure out the total capacitance. And we'll get here in a minute why this happens. Another formula, if I have just 2 caps in parallel, is product over sum. And product over sum would be, say, C1 times C2 over C1 plus C2. A little bit simpler formula. You just take the 2 capacitors, multiply them together, their capacitance for the top, for the numerator, and add them together for the denominator, do the division, you've got your total capacitance. Same thing with resistors in parallel, if you have just 2. If they are the same size, then 1/2 the value of one capacitor. So if I have two, say 10 microfarad caps, and I'm going to put them in series, I get 5 microfarads. That's it. So I get. If I've got two 8s, I get 4. If I got two 16s, I get 8. It's just 1/2 of one of them is be the total capacity, if they're the same size. If you got two of them, they're not the same size, you use this formula, and then you use the other formula if you got more than two. Now, why does this happen? Well, we'll go down here and we'll show why. These two guys are connected. These two plates here and these two plates of these capacitors are effectively connected together. Okay, so we've got lead going out to our circuitry, and then we've got this one and this one appear to be just basically two together, and then we come down to this one. Let's see, come down to the next one here. So this one and this one is this one, and this one will be this one, and we got this. Now, these in here are not connected to anything. They're just sitting in there. So they're almost acting like part of the, just a part of the dielectric in all effectiveness. The actual capacitance now will be from this point to this point. It'll be these outer plates. And the distance between those guys is basically what the capacitor, total capacitance, will be looking at, this distance here. So it's like two plates that's been spread considerably apart. This is basic theory, and it does work like this, but that's why it works like this, is because these two guys are not connected to the outside world at all. They're connected through charge carriers, through capacitance. So it effectively becomes just this one very wide distance between two plates capacitor, and that's why the capacitance is considerably less when you got capacitors in series. But basically just remember the formulas, and like I said, you can pause this at any point to see the formulas and write them down. Alright, some types of capacitors, really, you kind of know them, or you've watched enough of my videos and other people's videos. The old radios, the biggest ones you're going to run into more than anything will be paper caps. They'll either be in cardboard tubes, or they'll be encased in plastic. The newer ones was, but they're still just a couple metal, aluminum foil with paper in between that's got wax impregnated. Some had oil, like either castor oil or some other type of oil, used instead of wax. And they're just rolled up to make them smaller size. The other types is mica. Can be silver micas. It can also be tin plates, or even copper plates. There were different ones, but the most common were molded micas that you've seen people talk about. I've done a video on these about how to read the color code on them, but they call them dominoes. So there's just a piece of mica and plates on each side of it. There are ceramics. There are tubular ceramics. They're made out of a ceramic tube. They deposit a plate on at one end on one side, on the outside of the tube, and deposit a plate on the inside of the tube for the other connector. You have, of course, plastic film caps are just like the paper caps in design, except the dielectric will be some sort of plastic instead of paper. Electrolytic caps, that's the one I really want to concentrate on. The other two types basically are adjustable caps, like your patterns that you would adjust in alignment, both of either IF cans or the front end oscillator and the antenna RF. And then of course your tuning condenser. Everybody's seen one of those. The electrolytic capacitor, basically you're going to have, well, I'm going to show it as a just a plate made out of aluminum. Okay, that will be negative. But it actually is just nothing more than a conductor. It serves no purpose in the actual capacitance. You'll have some sort of material, usually paper in the older ones. Newer ones will have some sort of a porous plastic or spongy like plastic. And then you'll have another plate that kind of looks something like this. Okay, and it's aluminum. It's oxide aluminum, oxide coated aluminum. In other words, aluminum oxide on one side of it. And to gain more area, they roughen it up. So if you look at it real close, if you'd magnify it, it would start looking like hills and valleys and stuff like this. That, you know, all this becomes the effective area. So that's a lot more area than if I just had a straight flat piece. So it'll look rough. To give you an example of one, it'll have some grayness to it and stuff and look kind of roughy, slight. This is one here out of a electrolytic cap. Now in here, and I'm just going to draw just some dots or lines and dots and stuff. Now there were two types of electrolytics. There were wet, which had a basic can with a piece of corrugated or rolled up aluminum inside, and there'll be a little plastic insulator in there, and it was filled with liquid in it. Borax is what it really is in it. And then there's the dry electrolytics that is more from at least mid-30s on is the most common and used, and it's a paste. It's the same stuff, but then they add other ingredients to turn it into like a paste, and they get it basically pushed into the dielectric insulator, but it does interact directly, for all practical purposes, with this positive plate. And what it does is, as it operates, hydrogen bubbles will get on this plate, and that is your charge carriers, and well, basically is what creates a barrier and makes this plate positive. The electrolyte itself is the actual negative plate of the capacitor. So if this stuff starts drying out, you're losing your negative plate, is what you're doing. So that's what happens with electrolytics. They'll start to dry out. When they do, their capacitance goes down, because it's effectively like taking any other type of capacitor and taking one of the plates and start whittling away at it. So the biggest thing I want you to understand, this other aluminum plate is just nothing more than a contact. It's a conductor. It's just a way of connecting that electrolyte, that negative plate, and getting that charge into it and out of it. Whereas the positive plate is the actual capacitor plate, and it's got aluminum oxide coating on it that interacts with the hydrogen bubbles, and the hydrogen bubbles actually make up the actual dielectric separation. The electrolyte borax allows for it to basically become negative, because it will take a lot of its electrons and transfer them to these hydrogen bubbles, which then will come up against and attach to this positive plate. But after that happens, no more charge can move. Once it's fully charged up, then it will block like DC and work like a regular capacitor. But the most important thing is this electrolyte is, that I want you to understand, is the actual negative plate, and the oxide plate, aluminum, is the positive plate. And the other plate that is just regular aluminum, like this, is just a conductor. It connects this negative, the electrolyte, to the outside world. The biggest problem with these is that they dry out. And why do they dry out? Well, you put a capacitor together, then you got to seal it with something, and that's got to be insulative. Whether you got modern day caps or the old caps, the outer shell was always the negative. It'll be a can of some sort. Positive lead came out the center of a rubber or some sort of rubber piece that is fitted to one end of that can. The rubber deteriorates over time and starts letting air leak in. The air leaks in and starts drying out the electrolyte. Of course, temperature has a big influence on that. The hotter the cap runs, the quicker that action can happen. So anyway, that's electrolytic cap. And wow. Well, we'll keep going for a little while. So, capacitors and AC circuits. Well, right off the bat, when a capacitor's in DC, it just, for a moment, you have a current flow for a fraction of a second, and then it stops. The cap gets fully charged. That charge that's on the cap equals the voltage on the DC voltage you're applying. If it's a 9-volt battery, once the cap gets to 9 volts, end of discussion. No more current flow under practical normal conditions, basic conditions. But in AC, on the other hand, we're always flipping our polarity back and forth, so the cap never gets a chance to fully charge and block it. So as that polarity flips back and forth, the cap then consequently allows the AC through, but not easily. Again, going back to some of our losses, the hysteresis loss, the dielectric absorption loss, and things of this nature will have an effect on this. So a capacitor actually develops, when you put AC to it, has a certain resistance to that AC, and we call that capacitive reactance. So okay, there's a formula for it, and you'll see it. Capacitive reactance always is X sub C. Means capacitive reactance. It is measured in ohms. Now I'm going to show you the actual base formula. Then I'm going to show you a little bit different formula to work with numbers that may be a little easier to work with. The base formula is this. 2 pi FC. Okay. Capacity reactance in ohms. 1 over 2 pi, just constant, 6.28. Frequency, whatever the frequency of the circuit is, and the capacitance of whatever the capacitor is. These two in this formula, this will be in hertz or cycles per second. This will be in farads. But there is another formula where some of it got rearranged and some a particular number was put in place, figured out to frequency will still be in hertz, but the capacity will be in microfarads, which is generally what most of the time you deal with. So it's 159,000 over my frequency and my capacitance. Frequency again in hertz or cycles per second, but capacitance is in microfarads. Still gives me capacity reactance and ohms. Now, whenever I put a capacitor in a circuit, like an AC circuit where I got things flowing all the time, we go back to the old saying, Eli the Iceman. Ice is for capacitor. Current leads voltage. In a pure capacitive circuit, current will lead the voltage by 90 degrees. So current and voltage is 90 degrees out of phase. So there's a phase angle of 90 degrees. Now, I'm not going to try to draw a graph of that because my graph's not too good, but I will show what they call a vector analysis of it. This is voltage, and this is current. And this angle here is 90 degrees. Now, this is only in a pure capacitive circuit, which we generally don't always have. So we'll have other components in there, including resistors. And actually, technically, there is a certain amount of resistive loss in a capacitor. It's got leads, wire. There's wire in the entire circuit. And we also got those plates inside that capacitor which have to move the current for a while, through to get the charges in there. So there's resistance. But in practical or just under normal theory operation, if you had a perfect capacitor, no resistance in the wires, no resistance anywhere else, you would have an actual 90 degree phase angle. Now, what happens if I put and create a circuit where I have a capacitor and a resistor? AC line, generally the standard symbol for like a little AC generator or AC source, coming out, coming down to a capacitor, to a resistor, and back. Just a simple series circuit. This resistor has a certain resistance, whatever it is, okay? And the capacitor, depending on its size and the frequency of this, will have a resistance too to AC called capacitive reactance. The two combined create something called impedance. So, for this, Z is used for impedance. Again, it's in ohms. Equals the square root of my capacitive, well, we'll take resistance first. My resistance squared, whatever it is in ohms, squared, plus my X sub C squared. Now why is it? Why do we even use this formula? Well, if we look at, again, another vector analysis of what's going on here, because everything at this point, well, there'll be some what is known as vectors, and I'll get into that on the next video, what that is. But this will be X sub C, and this will be resistance. Impedance is going to come off this way at some sort of angle called, we'll call theta, just a little circle with a line through it. That's our phase angle. If I redraw this, because if I take a line down and a line across, I will find something quite interesting here. That, and actually I drew this just a little bit long, but if I take a line down through here and a line over this way, you'll come to that point. My drawing's not the best. But if I look at this line over here represents this, or this line represents this, they're both parallel, same length, parallel, same length. That's nothing more than really a right triangle. So, with one side being, say, R, the other side being X sub C, and this being impedance. So basically, it is your standard A squared plus B squared equals C squared triangle, or Pythagoras theorem. So you get Z equals the square root of R squared plus X sub C squared. Z is the hypotenuse. You take the sum of these two squared, take the square root of that, you get the length here. And that's really all impedance is. Which, by the way, on the first video, being my mind wasn't quite with it, I was thinking about something else on the video. Probably was thinking about the calculus or something. I know at the time when I got to that, I was also getting rushed because the battery was about to die on my camcorder, which is not going to happen this time because I got it plugged in. I wrote down something towards this effect, that Z, and we had three different things in here of like, oh yeah, X sub L, which is inductive reactance, minus X sub C, and I had them two being squared plus R squared. Okay, it's not exactly correct. The actual correct formula for this, when you have all three, is Z equals the square root of inductive reactance minus capacitive reactance, that as a unit being squared, plus R squared. I forgot the parentheses, so that was a mistake off the first one. This is the corrected here. Now, there is a phase angle, and I'll give you the formula for the phase angle. It's not hard to find or hard to do. It's cosine, and we just use the short version, of that theta angle that I showed between the hypotenuse and the resistance leg will equal R over Z. Okay, so resistance divided by the impedance of the circuit as it's drawn, numbers like this here. You take this resistance divided by this, gives you the cosine of theta. And you can find then, by using what is known as arc cosine, as just the opposite reversal of the cosine, you can find the angle. So if I take arc cosine of this, I get an angle. So that basically wraps us up. I'm sure there's going to be some questions on this. By the way, a lot of your scientific calculators can do cosine and arc cosine, of course, sine and tangent as well, and their inverse functions. But that's basically all that is going to be necessarily needed to know about capacitors. The next video I will do on inductors, because I get them out of the way, and then we'll start getting into dealing with series and parallel resonances and filtering circuits and such. In other words, getting deep into AC. And we'll look at some things that happens with resistance, both as a resistor as well as the resistance of the wire when we get in real high frequencies, so of AC. So anyway, I hope I answered for the most part at least some of the comments on the last video. If you still have questions, you can leave a comment, and I'll either get back to it on the comment itself, typing something in, or make a video or answer it in the next video. Then if you have any questions on this, of course, leave them in the comments, and if there's enough, I will either answer directly on there, or I'll just make, the upcoming video, I'll just put it in part of it. So thanks for watching, guys. If you like the video, give it a big thumbs up. If you're new to my channel, I do stuff like this, as well as restoring radios and TVs. I do videos on that. Test equipment. Everything is basically tube, vintage equipment, and stuff. So if that's something of interest to you and you like the video, not only give it a thumbs up, but if you haven't already subscribed, please subscribe, and then you'll get notification of new videos coming up. So anyway, guys, I'll see you on the next video. I'm not sure it'll be on inductors. Oh, well, AC part will be, but the next video will probably be either on TV circuits. Continuing on that, I think, is where we're at. Probably should be. And then, of course, the RCA radio. So, I'll see you guys in the next video, and thanks for watching. Have a good week. And thanks again.